It's Mrs. Hofferberth. Let's take a look at calculating heat in some more complicated examples. When we're doing our heat calculations, we of course need to keep in mind what equations we have to work with. So the first thing I'm going to do is rewrite our heat transfer equations, whether it's through phase change or through temperature change that we were using before. A couple quick reminders about these equations. For the phase change equations, you need to stop and think, should this be positive or should this be negative, depending on what the phase change is and whether your spacing and thus the potential energy is going to be increasing or decreasing. And for temperature change, remember that the change in temperature is the final temperature minus the initial temperature. That will ensure that you get the proper sign for Q. Once you have these equations ready to go, then you're going to be looking at situations where more than just one energy transfer is happening. So we're going to have both heating and phase change occurring within a single situation. First problem, how much energy do we need to take 10 grams of ice from negative 10 degrees Celsius to 40 degrees Celsius? When you have these problems, you need to stop and you need to begin by drawing either a heating or a cooling curve. That will help you identify what are the parts and pieces you're going to need in order to solve the problem. So for this curve, since I'm warming it up, it will be a heating curve. So my x-axis will be heat added, and we're starting at negative 10 degrees Celsius. We're warming our ice. So you should know that ice melts at 0 degrees Celsius, which means in order to take this into water, first I'm going to warm it from negative 10 degrees Celsius to 0 degrees Celsius. At that point, the ice is going to melt. And so remember, when phase change happens, what we see in the heating curve is a plateau as the energy goes into melting that ice. And then you are going to go from that 0 degrees Celsius water that you've now generated by melting it, and you'll take that up to 40 degrees Celsius. So as you look at this heating curve, you really see there are three distinct regions. Each region needs its own equation. And so the equations we're going to need to use, initially we are heating ice. And so we'll use Q equals mc delta T, but the specific heat we're going to use is going to be for ice. And then we are going to be melting it, which is the equation that involves the heat of fusion. And then we're going to be warming the water that results. It's really important to note that the specific heat for ice is different for water. It changes depending on what your material is. So we need some numbers for this. So for water, and all things about water, specific heat for ice, as that form of water, is 2.1 joules per gram degrees Celsius. For liquid water, it's 4.18 joules per gram degrees Celsius, and the heat of fusion for water is 334 joules per gram. You will be given these values. You're not expected to have them memorized. At this point, we have all the pieces that we need in order to calculate this. Each section, we're going to calculate the heat for, and then we're going to add them all together because we had to put all three amounts of heat in to accomplish the change that we were tasked with. I'm going to start with I'm going to start with heating my ice. Once I've heated the ice and I've melted the ice, then I'm going to heat up the water. And once I have all of these pieces known, I just have to add them together to find the total amount of heat that was needed. Last thing I'm going to do is take a look at my sig figs. When I do, I've noticed that I've been a little bit lazy. So my temperatures actually had information out to the 10th place, so I'm going to sneak those back in. And that's going to impact my sig figs in a couple of places. So for this first equation for the ice, it looks like for my 2.1 joules per gram degrees Celsius, I get 2 sig figs. And then I have 3 significant figures in the second equation that we used, and I have 3 in the third. All of these, the last significant digit is in the tens place. So I'm going to round my final answer to the tens place for 5,220 joules. Okay, let's take a look at a second example. So how much energy is transferred when 125 grams of steam at 105 degrees Celsius is cooled until it forms ice at -2 degrees Celsius? Just like we did last time, begin with the heating and cooling. So since I am cooling this from 105 to -2, that means I need a cooling curve. And so I'm going to have my x-axis be heat lost. I will be able to cool my steam down to 100 degrees. At 100 degrees, that is where it will condense to form a liquid. Just as boiling happens at 100 degrees Celsius, so condensation happens at 100 degrees Celsius. And then once all of my steam has been turned into liquid water, then I'll be able to cool it down further, down to 0 degrees Celsius, where I will have freezing occur, and then it'll take it down to -2 degrees Celsius once I have ice. So it looks like we're going to have 1, 2, 3, 4, 5 different regions of this cooling curve, which means 5 different equations. So for each of these, I'm going to label what we need. Initially, we are cooling. So this is Q is mc delta T. That C will be for steam. And then I'm going to have to condense it. So that's gas to a liquid. So that's going to be the equation that uses the heat of vaporization. But since I'm cooling it down, I do want to make a point that this is going to be a negative value. I'm removing that potential energy. And then we're going to cool it again. And then we're going to freeze it. But just like that last one, this is going to be a negative value. And then we're going to cool it one last time. Okay, so that's a lot of equations and a lot of numbers to plug in. Just like with everything else we've been doing, you will be given the values for heat capacities for all the different kinds of water or things that are in the problem, along with heats of vaporization and heats of fusion. So I'm going to list those now. And now that we have all the values that we are going to need to plug into these equations, it's time to work 5 different equations. So I'm going to do this, and then we'll come back on the other side. Okay, so that was 5 different equations. I calculated the heat necessary to cool the steam down, to condense the steam into liquid water, to cool the water, to freeze the water once we gotten down to 0 degrees Celsius, and then to cool the ice down further. So not crazy, just keep track of all the pieces, and then all you have to do to finish this problem is to add it all together. Please note, these are all negative numbers, so I should have a big negative number when I'm done. So let's do that. Okay, adding it all up, you get a negative 378,000 joules, which is negative 378 kilojoules. The last thing I want to point out about this is if you look at these numbers and these values, you'll notice that the biggest piece corresponded to condensation because you had such a huge difference in potential energy from your gas particles, which were really far apart, to your liquid particles, which are much, much closer together. And so there's going to take a lot of heat to accomplish that change. Okay, so when you have more complicated problems where there are not only phase changes and temperature changes, make sure you start by drawing a heating or a cooling curve. That's going to tell you what you need to do, which equations you need to use. And then once you've used those equations, you sum the amount of energy necessary for all the transformations.